For this afternoon, I'll be sharing with you concepts about digital, and I'll be introducing to you the concept of a DSP, or digital signal processing. So by the way, I'm Assistant Professor Christian Lucas, also affiliated in UPDSP Lab. For this afternoon, I'll be kicking off with the birth of digital information, some history, how the digital concept began and was further developed into various technologies. I'll be injecting some concepts in DSP, and I'll be showing to you some state-of-the-art technologies. And last but not the least, I'll show to you some projects done in our laboratory, and hopefully you'll be able to join them in your senior years in the future. So to start, I'd like to share some quote from a famous mathematician, Claude Shannon. He said that information is the resolution of uncertainty. So why is it a resolution of uncertainty? So in his book, Mathematical Theory for Communications, Shannon actually treated signals or phenomena as random variables or random processes. Now, from these unknowns, when you try to model and look for patterns, you begin to resolve some useful signals out of it. So these signals are what we call information. So hopefully what Shannon has achieved is this signal, this information is quantifiable and communicable. So all of this can be found in his book, Mathematical Theory of Communication. And as I've said, it discusses about quantification and storage and communication of information. And he uses entropy as a measure of information, which you will see later on. And he treated this information as elements in a random process. And some of these values, discrete values, can be modeled as random variables and can be computed as such. So he coined the word bit, referring to binary units, since he was able to represent most signals, most systems in binary units. So here is Shannon's entropy equation. So this denotes the amount of information, the amount of bits you need given n number of values with given probability values p sub I. So he's stating here that you can compute for the minimum number of bits in order to accurately represent a random variable with the given probabilities and no number of levels. So let's try. Given a symbol with 5 possible values, A, B, C, D, and E, with probabilities 0.5, 0.2, 0.1, 0.1, 0.1, what is the minimum number of bits to accurately represent this information? So plugging into Shannon's equation, we just evaluate the summation. So I'd like you to try it out. So for this exercise, you just need to multiply the probability with the log base 2 of that probability, and you add that for all the values. So first, the value A, you have 0.5 times log base 2 of 0.5, plus for the value B, you have 0.2 times the log base 2 of 0.2, and so on. So you'll get 1.9, or roughly 2 bits. So you need 2 bits in order to accurately represent this symbol with 5 different values. So with that, you are able to convert, you're able to quantify information in binary. And that is what Shannon equation has been able to achieve. And this was the basis for most of communication systems and digital systems. But as you can see, there are some practical issues here. Number one, when we're dealing with real-world signals, you have infinitely many values. For example, if you're measuring voltage, you get to measure a lot of different levels, a lot of different ranges for voltages. So how will you represent them? If you have infinitely many values, theoretically you have infinitely many number of bits, and you can't do that for most systems. So how do you accurately and faithfully represent these continuous signals? Number two, symbols and states are functions of time. These values change throughout time. And once you discretize information, you need to properly get the right information, the right time information of these signals. So how would you correctly represent the time information of these continuous signals? Next, the probability models are imperfect. So we're dealing with the piece of ice. But as you'll know later on, especially in EEE 137, that most of the models that we have are empirical in nature, and there are limitations to the accuracy of the models that we will use. And last but not the least is that one of the major concerns of Shannon during their time, the availability of machines that can quantify, store, and process the digital information. So before, they don't have gigabytes of storage. They don't have gigabits per seconds of speed. So we'll see these examples of machines as they evolve through time later on in my presentation. So actually, the issues 1 to 3 were answered also in his book. And those concepts are actually the fundamentals of DSP. So let's take a look at an example for audio A to D conversion. So at your house, or for example in my setup, I have this microphone beside me capturing my voice, and it translated to a digital signal that goes in through my sound card. And when it gets to my computer, I get to process it, have some effects, transmit it, and I can also play it from this computer to my monitor speakers. One question I like to ask first is, when we talk about acoustics or sound pressure, we have infinitely many values, infinitely many pressure values. So how do we represent these values digitally? So looking back at Shannon's idea of discretizing signals, we can actually discretize values of continuous signals. That process involves what we call quantization. So it's a process of converting continuous valued signal into a discrete valued signal. For example, if I have this reading of my voice, and then I'd like to represent it into 8 levels, so using Shannon's formula and assuming that these 8 levels are equiprobable, meaning each of them has equal chances, which means the probability is 1/8 or 0.125, I can get 3 bits to accurately represent this signal. However, if you notice, for example, at time index 6, wherein the value is rounded to 7, the actual continuous signal is somehow or somewhat higher, a little bit higher than 7. So that would be a problem because you already have what we call a quantization error. And it's a difference between the original versus the sample digitized signal. what do we do about this quantization error? Can we recover the lost information? Well, the answer is no, because we're trying to map continuous values to discrete values. And when we convert things from continuous to discrete, we get to truncate, we get to round off. And that's one of the bad things about digital. And we cannot recover it, but we can actually increase the bits in order to reduce the quantization error, but not too high, because using too many bits will result to actually more delays in your system because it will require large memories, large storage, large buffers. Okay? So it will congest your internet connection. It will congest your network. So there is a balance, or there is an optimal condition for the number of bits to use in quantization. Next, I'd like to ask this about the same example before. When you have sound waves, they actually change quickly over time. So the question is, we need to preserve the right time information, right? What should be the speed, or how fast should we convert the acoustic information in order to capture the proper time information of our discrete signal? So what deals with this time information is what we call sampling. So sampling is the conversion of continuous signal into discrete time signal by taking brief instances of that analog signal every t seconds, which is also known as the sampling period. So when we have this particular waveform, a sinusoid, and we try to sample it 10 samples per second, so we get this figure on the right, upper right, wherein we can get somehow faithful representation of that sinusoid. If we sample less often, so just 6 points in a second or in a cycle, we can see that it becomes more jagged. And at 2 points in the cycle, you can just see almost just the peak, the max and the minimum. So we see here that when we use lower sampling rate, the signal gets poorly defined in time. And the consequence of this is that maybe some information will not be considered, some information will be lost. So there's actually a theorem suggested by Nyquist and Shannon that when you have a signal with a maximum frequency component at Fa, then the sampling rate should be at least twice that component, that Fa, in order not to lose information. So this is one of the strict rules in DSP. Fs should be greater than or equal to 2Fa. So if you have an adequately sampled signal, you get to have faithfully represented digital signal. But if you undersample, such as the figure below it, so you can see that the high frequency signal becomes a low frequency signal. And this misidentification of a signal is what we call aliasing. So I suggest that you watch this YouTube video for an interactive audio demo of aliasing. You can observe what is happening on the figure below, which is a high frequency signal aliased into a low frequency signal due to undersampling. So in music applications in audio, we get to encounter this a lot. For example, in CD players, I don't know if you've encountered it or have seen it. Compact disc actually have sampling rates of 44.1 kilohertz. And that is because the maximum frequency component of audio in human hearing is 20 kilohertz. So multiply that by 2, add some leeway. So you have 40, roughly above 40, so 44.1K is good. And comparing it to human speech, which is just until 3 kilohertz, the minimum required for human speech is roughly 4 times 2, which is 8 kilohertz. So depending on the application, that's why your hands-free audio, your headset, your call quality is much lower quality than your music player, is because telephone quality is assumed to only have a maximum frequency of 3.2, comparing to MP3 players expecting until 20 kilohertz. You can also see here that the number of bits, if you try to multiply the sampling rate with the number of bits, you get the data rate, which is the number of bits per second. And of course, when you have high fidelity music, you're running at a higher sampling rate and use high number of bits, you get a lot of data rate. So you have, for example, 706 kilobits per second as compared to telephone quality, which is 8K times 12 bits, which is roughly 96 kilobits per second. And when you do compounding, later on in your higher years, you'll be able to see compression and expansion of on digital signals. You get to lower the bits without much reducing the quality of the signal, and you get to compress the data rate. This is what's happening in your YouTube, in Netflix. So without compression, we'd all be congesting the internet, the bandwidth of the internet. So it's because of these techniques, the compression and reduction of bits, reduction of sampling rate, that we are able to have multiple clients using the same service all at once. And we also have this speech encoding in LPC using just 8K and 8 kilohertz and 12 bits, was able to achieve a very low data rate, but there is actually a use of this, especially in long distance transmission and in limited scenarios of telephony. So what happens if I sample less often? So having a sampling rate of less than twice the maximum frequency will always result to aliasing, and you wouldn't want it because you actually lose a lot of information. And what if I go up? What if I use very fast sampling rates? If I use a very high sampling rate, I'll get to use a lot of memory and storage. So for example, you have 16 bits of quantization and 44.1 kilohertz, you'll have roughly 88.2 kilobytes per second. That would mean a 3-minute song would cost you 16 megabytes. But if you do compression and reduction of sampling rate, you can actually achieve lower than this. So if you have noticed, your songs are actually compressed roughly around 4 megabytes to 5 megabytes. They actually use what we call variable bitrate compression. So most of you have probably used this at home, enjoyed the convenience of having a digital TV at home. If you compare it to analog TV, which is super noisy, you might wonder, how do these digital television receivers correct information? How are they able to smoothen out the image to accurately reproduce the signal over long distance transmission? So they actually model the probability of the channel, the corruption in the channel, and what this is what they call channel coding. And they use error detecting or error correcting codes in order to achieve a more reliable communication over the transmission channel. It uses the probability models. And this is what you can actually take as your elective in the future. The block codes, continuous codes, which are just practically of the same purpose but different applications. So block codes are actually appending the checker bits at the end of your payload. However, convolutional codes or continuous codes are added to the actual structure of the code word. So you get to check the matrix operations for this. So for example shown here, you have a generator matrix cross multiplied to your message, and you get this code word plus the checker bit. So you have this generator matrix that you need to have in both the receiver and transmitter in order for you to accurately detect your errors and furthermore correct them. Same goes with convolutional codes. So convolutional codes uses these generator polynomials. Usually they use XOR gates or modulo 2 operators to generate these checker bits. So later on in your EEE life, you'll get to encounter this. And my point is that these codes are needed to detect and eventually correct your errors in your communications. I can opt not to include them, but if I don't include correction codes, there's no way to correct the received information, which is most of the time in actual scenarios. The signal gets corrupted and you lose a lot of information. But if I use so many bits for error correcting or error detection, it will also induce more delays, and it also requires larger memory capacity and storage. So these are the things that Shannon discussed in his book, and most of these are actually being pushed to the limits in wireless communications. So for the last part of my presentation, I'll be showing to you examples of digital computing machines. So how did we transition from the very first computers to standalone DSP chips? If you've already read about Alan Turing, he was the one who conceptualized the Turing machine, a machine capable of finite set of configurations as early as 1936. He was actually developing this during the war, and if you watch the movie about him, it's basically used against their enemy, the Germans. All right, so this machine was able to decode things and were used by the military. And it was contested actually if this machine was the first or the Z1 by Konrad Zuse in 1938. Zuse was able to construct a mechanical device, a mechanical machine that can compute 22-bit floating point, 9 sets of instructions, and can operate 1 to 20 cycles per instruction. It actually developed into Z2 and to Z3 and was later on commercialized. This is actually the first programmable computer invented. So for the transistor computers, since transistors were patented in the 1940s, 1950s, the first transistor-based computer was done in Bell Labs in 1954. Transistor digital computers. Next would be the Harwell and the TXO by MIT. The first commercially available transistor computer was by IBM. by the IBM 608 in 1957. And going through the years until 1970s, they were able to push the development of semiconductors, the MOSFETs, and the microcontrollers and microprocessors. So this was the golden age of DSP. By that time, the fast Fourier transform by Cooley and Tukey was already published, as well as the linear predictive coding, as well as discrete cosine transform used for video broadcast and communications. By the later years in 1975 to 1980s, we have this development from the bit slice chips to first standalone DSP chips in Japan. So as shown here, this TMS320 DSP chip used for guitar effects. If you've probably used some. So they're using DSP chips. So right now in 2020, where are we? So in 2020, we already have these types of technologies, more smarter technologies such as the neural processing units. We've already gone beyond DSP. We've gone to AI with more multimedia sensors, which computes billions of instructions per second. We have a lot of application in audio, in mobile, such as this smart hearing aid. As you can see, we also have a lot of technologies intertwined along with it: signal processors, antennas, transducers, microphones, batteries, and so on. And these devices are small. These devices are becoming much, much smaller and faster and smarter, such as the filters that we have in Snapchat or Instagram. So in DSP, we actually developed this voice recognition softwares. Can translate Filipino speech into text, and actually we also have the synthesizers, which converts the text into voice. We also have this road network extraction using image processing. These are from satellite images. So we get to play along with the satellite image data, and we extract some valuable information to it using image processing. There are a lot of technologies nowadays that use DSP in that it has evolved much more, especially into AI and machine learning. So if you're actually interested in these fields, you might want to inquire applying in our lab in the future sa 4th floor ng EEE, UP Digital Signal Processing Lab, right? Rooms 406 to 412 in our old building. And you can actually email us for questions, for consultations, for applications. And some of our faculty, I believe you've seen Dr. Franz De Leon for the orientation. He's our current lab head, and our previous lab head, Dr. Randy Cajote, specializing on image and video. The founder of the laboratory, Dr. Rowena Guevara, who is also the undersecretary right now of the Department of Science and Technology. And here we are, the junior faculty. Most of us have masters. One is ongoing PhD and one is ongoing MS. So right now we're specializing in multimedia fields, but we're also doing consultations on other fields such as biomed and satellite processing. So these are some of our priority areas: multimedia, finite element simulations, numerical simulations. We also do natural language processing, and we help other fields as well. So any data that you can convert to digital. We can play with it, we can do analysis with it, and we can do some valuable information to it. Okay, so thank you for listening.